Hey everyone, welcome. Today we're tackling a Leetcode problem called maximize the number of target nodes after connecting trees to. It sounds a bit involved with two trees and queries, but don't worry, we'll break it down step by step. So here's the gist. We have two trees. For each node, let's call it in the first tree, we imagine connecting it to some node in the second tree. Our goal is to pick that connection in the second tree wisely. Why? Because we want to maximize the total number of nodes that are to our original node. A node is to another if the path between them has an even number of edges. And a node is always target to itself, because that's 0 edges, which is even. We need to do this for every node in the first tree and return an array of these maximum counts. Each query is independent, meaning the connection we imagine is just for that query. Let's look at an example. Imagine the first tree has 5 nodes, and the second has 8. If our query is for node 0 in the first tree, we connect it to some node in the second tree. The best we can do results in 8 nodes being target to node 0. If we consider node 1 in the first tree, the answer is 7. The key is figuring out how this definition works with distances and how the connection plays a role. Okay, so when we connect node from the first tree to node from the second tree, we're essentially adding one edge. The nodes target to Watambasambakprutu will be some from the first tree and some from the second. From the first tree, these are nodes where the distance from Sakra to within the first tree is even. From the second tree, these are nodes where the distance from all the way to is even. This path goes then the new edge to then through the second tree to. The length is 1, for the new edge plus the distance from Tark to in the second tree. Trying all for each, and then calculating distances for all nodes. Sounds like a lot of work, probably too slow. Here's a neat trick. Trees are what we call bipartite graphs. This means we can color their nodes with two colors, say black and white, such that no two nodes of the same color are directly connected by an edge. A practical way to do this is to pick a root, say node 0. All nodes at an even distance from this root get one color, e.g. white or color 0, and all nodes at an odd distance get the other color, e.g. black or color 1. So for any node in the first tree, the nodes that are target to it, meaning an even distance away within the first tree, are precisely those that have the same color as if we've colored the first tree, starting from its node 0. So if node is all other nodes are at an even distance, if is all other nodes are. This gives us the first part of our answer really quickly. We just need to count how many nodes of each color there are in the first tree. Now for the second part. Nodes in the second tree. The path from Gaskematu is then the new edge, to then the path from Gaskematu. The length is 1 plus the distance from Gaskematu. For this total length to be even, the distance from Gaskematu within the second tree must be odd. Let's say we color the second tree from its node 0, getting uncounts. If we connect to a we need, since we can choose it to be like node 0 itself in tree 2, or like a neighbor of node 0 in tree 2, if one exists. This means we can always aim for the larger of the two color groups in the second tree. So this part of the answer is simply the maximum of the counts of nodes and nodes in the second tree. Alright, here's the Python code for this approach. It looks like a bit, but the main idea is that helper function. Let's call it getColorData. We'll break that down. Then we use it for both trees and combine the results. This helper function, let's call it getColorData, is key. First, it builds an adjacency list, which is just a way to know which nodes are connected. Then it does a breadth first search, or BFS, starting from node 0. As it explores, it figures out the distance of each node from node 0. If the distance is even, it's one color, let's say color 0. If odd, it's color 1. It stores these colors and also keeps a running tally of how many nodes of each color it finds. Finally, it returns the list of colors for each node and the total counts for each color. Now, in the main function, first we call our getColorData helper for the first tree. This gives us the color of each node in tree 1, and the total counts of nodes for color 0 and color 1. Then, we do the same for the second tree. We mostly just need the counts of color 0 and color 1 nodes from it. The contribution from the second tree, as we discussed, will be the maximum of these two counts, assuming the second tree isn't empty. Finally, we loop through each node in the first tree to answer the queries. For each we check its color in the first tree. If it's, say, color 0, then the first part of our answer is the total count of color 0 nodes in tree 1. If it's color 1, then it's the total count of color 1 nodes. We add this to the contribution from tree 2, and that's our answer for node. So how efficient is this? The coloring part for each tree involves a BFS, which is proportional to the number of nodes plus edges. Since they're trees, the number of edges is about the number of nodes. So that's about order n for the first tree, where n is its number of nodes, and order m for the second tree. The final loop to calculate answers runs n times, but each step is super fast, just a lookup. So the total time complexity is big O of n plus m. That's really good. For space, we store adjacency lists and color arrays, which also take up order n plus m space. So to wrap it up, the problem asks us to find nodes at an even distance. The big insight is that trees are bipartite, so we can use a two-coloring scheme. By coloring each tree based on distances from a root, like node 0, we can quickly figure out counts. For a query node in the first tree, the number of targets in the first tree depends on color and the total count of nodes of that same color. The number of targets in the second tree relies on us picking an optimal connection, which boils down to taking the larger of the two color group counts in the second tree. This coloring approach gets us a very efficient solution. Hope that breakdown made sense. If it helped you understand the problem and the solution, maybe hit that like button, or subscribe for more explanations like this. If you have any questions, feel free to drop a comment. And hey, if you're feeling generous, there's always the Boba Fund. Keep practicing, keep coding, and I'll catch you in the next one.